Another example here. We have a horizontal spring. It has a spring constant of 100 newtons per meter. It is compressed 20 centimeters and used to launch a 2.5 kilogram box across a frictionless horizontal surface. After the box travels some distance, the surface becomes rough. The coefficient of kinetic friction between the surface and the block is 0.15. Oh dear. We want to use work and energy to find how far the box slides across the rough surface before stopping. So let me draw a sketch. Here's my equilibrium. The box was compressed against the spring so that the spring had an initial compression of 20 centimeters. So some external force totally had to push that box against the spring. But now we're going to release it from rest. I'm not sure why they have us. It says it slides for a while where it's frictionless, and somewhere down here it becomes rough. Meaning now there is kinetic friction. The problem wants us to know how far the box slides across the rough surface before stopping. So essentially it wants to know this distance that has friction. And stopping, the box will be V final over here at this location. Okay, so conservation of energy, our fundamental equation. I know the forces acting on the box are the spring, which we're going to account for. I'm sorry, I don't know what I did. We account for the spring in terms of potential energy. Gravity, we account for in terms of gravitational potential energy, which in this case, since the floor is horizontal, we have y initial equal to y final. So gravitational potential energy will not come into play. Motion is accounted for in terms of the kinetic energy. The other forces we have a normal force, but remember the work done by the normal force is always zero, and that's because the angle between the normal force and the displacement overall is 90 degrees. If the force is perpendicular to the direction of motion, there's no work done by that force. And then kinetic friction, we're going to account for in the delta E thermal term. So we can say work external is zero, but we need to consider potential and kinetic energy initially, and then how much thermal energy is generated or transformed from the energy before. So I'm going to choose my initial moment in time to be this point when the mass has been pushed against the spring, compressing the spring by the 20 centimeters. At this moment in time, the spring is compressed, so the spring mass system will have energy because we know the spring is going to push on the mass. Gravitational potential energy, we can just call zero. We can say this lowest point where the whole problem takes place is y equals 0. Kinetic energy initially is going to be 0 because we're talking that split second we release the mass, it's not yet moving at that instant. Now the final moment in time, I'm actually going to put way over here when the mass has stopped. The spring is not connected to the box, so there's no spring potential energy. But the nice thing is it doesn't matter if the spring's not connected the whole time. We do not need to break energy problems into pieces. We can look at any two moments in time as long as we're accounting for all of this energy, any type of energy there could be. Gravitational potential energy would be 0 because we haven't changed height at all. Kinetic energy would be 0. So at first glance, this is a little weird. Initially, we have energy in the spring, but at this final moment in time, we don't have any of these. But thermal energy, as the box slides along the rough surface, the potential energy that has been turned into kinetic energy, the kinetic energy will now turn into thermal energy. So we have all of this initial energy stored because of the spring being compressed. We're going to set that equal to the thermal energy that's generated. Now, thermal energy is the force of kinetic friction times the distance the object slides. So I labeled it D in our picture. So we want to know how long this rough patch is in order where it stops the box. So force of kinetic friction coefficient times the normal force. We do need a little free body diagram. So normal force, mg, while the mass is over the initial point, there's going to be a spring force. And then later down here, there's going to be a friction force. But still normal in mg. Since there is no acceleration in the y direction, and we're on this horizontal surface with no other vertical forces, the normal force will equal mg. So we can say this force of kinetic friction is that coefficient times mg. I'm going to plug that in over here for my friction. So that's my force of friction. In order to make this thermal energy, I need to remember d, the distance friction acts over. And quite honestly, forgetting d is one of the most common mistakes. So just a heads up. We have spring constant, we have that initial compression distance, we have mu, we have m, so we have everything except for d. So I'm going to just solve for it. So the 1/2's already there, the ks squared, and I bring the mu mg to the other side. So K is 100 newtons per meter. Our initial compression is 20 centimeters, but that needs to be in meters for our units to work out. The coefficient is 0.15. That does not have units. The mass of our box is 2.5. G is 9.8. So let me plug this into my calculator. Getting 0.544 meters. Let's see, we have maybe 2 sig figs. So 0.54 meters. We could say 54 centimeters, that's fine. But we do need the distance in S to be meters in order to work out with the units of K being newtons per meter. So for the units to work out, we need to put everything in terms of SI units to begin with. Now, by the way, if the whole floor was rough, this box would have slid 54 centimeters from that initial compressed position. The rough patch did not necessarily need to be all the way far away. I'm not sure why this particular problem chose to do it that way, but the approach to the problem would be the same even if the friction was all the way on the whole floor. And D would be the distance the box slid while friction was acting on it. The setup would end up being the same.